15 seconds. Guidance internal. 13, 12, 11, 10, 9, 8. Ignition sequence start. Engines on. 5, 4, 3, 2, 1. All engines running. Launch commit. Liftoff. We have liftoff at 9:34 a.m. Eastern Daylight Time. The tower is clear.
And we have a roll program. Roger. We have good thrust on all 5 engines. Plane throttle, roll complete. Roger. And we have 50 program. Roger.
Okay, I think we need to move on. Cline, Frasier from NASA, JSC. Thanks. We'll have time for other questions later on.
Can I shut this down, okay? Oh, I see how you said it. Let me just shut it down. I've been out of the space program since about 1973, and it's really fun to be back and see all the old, a lot of faces and see how many people have been still excited about the program. And I thought one of the things I would do is I would come. Oh, excuse me. One of the things I thought I would do was to come in the standard uniform of the NASA engineer of the 1960s. Even though we lived in Houston, where it was the weather was even worse than here, this is basically what we wore day in and day out. And if you didn't wear a tie, or in some cases, some of the senior people began to grow a beard toward the end of the program, you were corrected by the senior management. Now, when Richard asked if I wanted to say a few words for the conference, my initial reaction was, gee, you know, what is it I had to say about digital computers? I don't really have to say much because my role in the program was more as a semi-technical program manager at Houston and a few other things. And then I asked him, I said, well, nobody's ever told the story of how we happened to switch from an analog autopilot system to a digital autopilot and make Apollo the first manned digital flight control system ever. And would that be of any interest? So here I am. Now, to put everyone back into what things were like, digital computing in aircraft and spacecraft and digital flight control was not always the norm. We think about it now, but when Apollo started, the mean time to failure for a really good inertial navigation system in an aircraft was about 15 hours. Okay, digital computer inertial system, not too good. And digital computers in airplanes were just flat not to be trusted, and even fly-by-wire was suspicious, and you would only use it if there was no possible way to string cables. And anyone who would suggest something as critical as flight control be trusted to a digital computer at that time would have been treated with even more skepticism than the people who proposed lunar orbit rendezvous early. I mean, it was just totally out of the question. And again, to kind of frame that, even in 1970, when I was leading the team to look at space shuttle electronics and lay out the configuration there, the idea that we would talk about digital flight control in the space shuttle was argued vigorously by many people that said for something, maybe you got away with it in Apollo, but for something as dynamic and critical as a space shuttle, you know, you just can't do it. And that only got finally put to bed when we managed to get the folks at Dryden to take their F-8, and we gave them some what I would call pre-owned Apollo hardware back from one of the flights to run a digital flight control demonstrator in an F-8, which is single-engine high-performance interceptor of the time. Now, what I want to do is to talk more about how, rather than any technical talk about what the autopilot was like, what was going on in the management sense and how this actually able to happen, because all of you know what it's like to get technical change pushed through an organization. And as I look back, I think the absolutely essential ingredients for us to make the change were, first we had intractable command module problems in terms of weight and reliability. The stuff wouldn't fit at the time. There was an outsider's view that came into play. There was a talented technical team available that we could have as a resource. A lot of luck, just a lot of luck. But most importantly, we had leadership that was technically secure enough in their own skins to go ahead with this. That they didn't, in spite of the fact that all the experts of the time said it would not work. Literally all the NASA flight control experts, everyone else said it would not work. So I want to take you back a little bit, go back 43 years to 61. As Eldon said, MIT picked up their contract in August, and they were committed to design the primary onboard guidance and navigation system for Apollo. And their basically approach was to take their Polaris inertial system, make a new computer, add some optics, and go forward. Now in 1962, then North American got picked for the command and service module, and their design, they were encouraged, let me put it that way, to use the MIT GNN as a piece of GFE instead of going off and developing their own. And they came forth with a pretty conventional system. You have a guidance system, you have a flight controls with rate gyros and all the electronics to provide stability. And then they also had a set of attitude gyros to be used for the astronauts to manually kind of control a long burn in the event the primary system failed. And then there was one final system which was would hopefully allow a manual reentry from at translunar speeds in the event the primary guidance system didn't work. Now the good news here is that we didn't ever have to actually try that, but the other piece of the thing that was going on at the time, we had a long mission time, 14 days. Electronics weren't too reliable, so the approach to getting reliability was in-flight repair. So to try to design with common modules and to carry along spare parts and have the flight crew replace them as they go. Now, I think now, and you look back, and everybody would laugh, but then it was what seemed to be the best course. And I can still remember a trip up to the lab must have been December 1962, with I think all the original 7 astronauts were there, and they were part of the briefing was this in-flight maintenance business. And I can still remember their reaction was, "You've got to be kidding," you know, or something more vocal than that, for just the in-flight maintenance of the guidance and navigation system. But NASA still held to the in-flight maintenance for a while. But then in June of 63, well, and 62 ended with, it was interesting times. We lived in Houston, and we were within range of the missiles that the Russians were installing in Cuba, and there was the missile crisis. And we were being prepared to load up our wife and kids and get out of there. Now, in 63, we had a few electrical failures during one of the Mercury flights, and that pretty much convinced everybody that you had to seal all the electronics to make them waterproof. And if you think about what goes on in a spacecraft where you've got zero gravity, you've got this moisture floating around, you've got cold plates, as Eldon said, well, where does the moisture collect? It collects in the cold plates. And where do you have connectors and other things on the cold plates? So you have to really seal that stuff up good. So in-flight maintenance went out, and we started over again. Now then Grumman was picked for the lunar module, and again they did a fairly similar thing. They had to use the MIT primary guidance system, much to their displeasure, but that was one of the breaks. But then they had a fairly conventional control system being fed by the MIT system, and then they also put in a strap-down inertial reference system to be used for an abort-only case. But both systems were feeding through a redundant Grumman-designed conventional analog system. Now, one of the other things that was going on at the time was there were quite spirited arguments going on between particularly the folks at MIT, Milt Trageser and the NASA people responsible for the manned spaceflight network about what the navigation accuracies were going to be, because Milt was he was in the world that said, boy, we have to do this from on board. We have to be self-contained. What happens if we get interruption from the ground, and besides the radars from the ground are not going to be accurate enough? And at this time, the really accurate atomic clocks were coming along, and the ground people were saying, gee, you know, with what we can do, we can provide pretty accurate navigation all the way. So then we were in the North American, oh, wait a minute, I'm going to get ahead of myself. But it was really kind of fun to watch the people go argue back and forth, and since nobody had ever flown these things, of course, that made the arguments a lot hotter. Then in late '63, a new management team came to Houston. Joe Shea came down from NASA headquarters, and he brought with him Cliff Duncan, who'd been with DARPA, and he brought Cliff down to run the guidance and the navigation and control parts of the NASA. And the reason I mention that is that these two people were absolutely critical to the fact that we were able to make the decision to change. And then, of course, the year ended with the President Kennedy's murder in Dallas, and everybody was on a down note at that time. So now we moved to '64, and Cliff is there new, and he says, let's go around, let's take some people around and look at what's going on in the guidance navigation control system for the command module. And so he put together a bunch of people who were interested, some of the people who'd been running the project, I think one of the astronauts, and a couple of people from the Air Force, and I was included in that because at the time I was working over in the astronaut organization providing some engineering support for that, so I kind of went along. Now, when we got to Honeywell, and Honeywell's a North American contractor for all the stabilization control system, and they laid out what they were thinking and what they were doing and how they were going to handle the redundancy with no in-flight maintenance and how much gear they had to have. And it became immediately obvious that it wasn't all going to fit, and they didn't have a concept that was going to work, but that was okay. We're keeping going down the road. And if you looked at the system, what it included, the optics, the gimbal inertial platform, the MIT system, had two of these guidance computers in it. And then it had all the redundancy in the stabilization control system and this other display. And some total of either, I'm not quite sure, it's either 13 or 16 gyroscopes and 5 accelerometers. And at the time, those are all fairly trouble-prone instruments. They may still be, for all I know. And so there's some concern about that, and the things were just too heavy to fit. Now, again, looking back, you had NASA, these experienced companies, North American, Honeywell, MIT, all committed to an approach, pretty conventional approach with a low risk as far as the configuration is concerned. So it isn't going to work. Now, I arrived at NASA, if I digress a second, I arrived at NASA in mid-62. And I was fresh from working on the design and reliability for nuclear weapons. So, what did I know? And I knew nothing about space. My only really relevant experience had been a lot of work with analog computers and radars for 90mm anti-aircraft cannons to shoot down airplanes. And I found it prudent to not mention that bit of experience around NASA because this was not very popular with people who flew airplanes. and I worked for a guy who was an ex-P-47 pilot, and his boss had flown everything from P-47s to B-29s, and of course the astronauts were there. So that was one bit that got hidden. Now, in this round-robin meeting at Honeywell, as I was sitting there, the light bulb kind of came on that we might make the Block 2 command module a lot simpler, lighter, and more reliable if we'd make a change in configuration. And let me, if I step back just a second, one of the things I said was that there were two of these computers in there. The reason there were two computers in the command module was that I guess they'd found a way to make them fit, but that Eldon and MIT were really concerned about the onboard navigation, and how could you make the navigation work if you didn't have the computer, and so we would have two computers on board. So as I was thinking about changes, I thought, well, again, not knowing enough to be scared, I guess, that we could maybe extend the guidance computer to do the flight control work and just make that one string, and then have Honeywell have a single string analog flight control, and that would simplify all the switching and all the considerations that were going on. And it would eliminate a lot of the redundant electronics, and if you made some changes to the Honeywell system to extract angular rate data from their body-mounted gyros that were going to be used to help with this backup engine burn, you could eliminate the rate gyros, so we'd get rid of one complete gyro type. And then thinking, well, we've got these attitude gyros that are already in the spacecraft, and you've got this display thing for a manual reentry, which had a 2-degree freedom gyro and accelerometer. With a little bit more circuitry, why couldn't we just use the information from these body-mounted systems to drive this other display? And so we could just kind of carve out a lot of various pieces. And then finally, since the Manned Spaceflight Network people were saying how accurate their system was, and that in spite of all the arguments, everyone had been able to agree that that would be the way we'd do backup navigation in the event the onboard system totally failed. If it's good enough to do backup navigation and get people back, why couldn't we just use it as a primary navigation, make the onboard system the backup, and eliminate one of the computers? And it seemed like a reasonable question, and it looked like we might be able to both save weight, simplify the redundancy management, get rid of 2 gyro types, an accelerometer type, and just get the overall parts count down, and it might all fit. Now, at the time, I was 29, a very junior GS-13 with no GNN credentials. I didn't have the nerve, I basically didn't have the nerve to say anything this heretical during these meetings. I mean, I knew exactly what would happen to me. So I got back to Houston and did some scratching about reliability diagrams and from my nuclear weapon days, and looked at the Minuteman I computer and the Minuteman I system because I knew that it was using a digital flight control. And it seemed like the Minuteman I was likely to be a more dynamic environment than the command service module. And so if they were using a computer that was a lot less capable than the AGC, the Apollo guidance computer, why couldn't we fit it in? So then several weeks later, I was one of these typical big program meetings. You've all been to these program review meetings. And part of the meeting involved hand-wringing over what to do about the stalemate resolving the North American Honeywell design issues. And so then during a break, I can remember going out of this big conference room, and Cliff Duncan was about as, if anything, he was taller than I am, but I talked to him, and I screwed up my courage and kind of briefly sketched out, you know, what might solve the problem. And I'm thinking back on it and talking to my son, thinking, you know, if I'd worked for Cliff, I didn't. I was over in the Crew Systems Division, but if I'd worked for in the Guidance and Control Division, I would never have been able to do that and never be able to put the ideas out because they would have to go up through my boss, and they were all the flight control guys who absolutely knew this stuff would not work. And so it would have been, go off and do a study and it will never see the light of day. But that wasn't the case. And I've always been grateful to Cliff Duncan, that he didn't look at me like I was just a total nutcase and walk away. Instead, he said, come see me and fill me in with some more details, which was a fairly unusual thing in my experience. Now, what I then now my memory is kind of blank about the next couple of months because a lot of things were happening. But what I remember is that talked to the MIT people, MIT management, and the reaction they had was, we can't do it. And I don't know how much of that was driven by, I know a part of it was driven by the fact that they already had an awful lot on their plate and they were under very heavy schedule pressure. And part of it, I'm sure, was we've never done this before. So MIT management didn't think they could do it or didn't want to do it. The Houston flight controls people, absolutely sure digital flight control would not work for Apollo. Just absolutely sure to a person. But Joe Shea decided, he was program manager, that he could solve some of the problems by making these changes. So guess what happened? He called North American in and told them this is what we're going to do in no uncertain terms, and that we're going to have digital flight control. We were going to make the Manned Space Flight Network the primary, and they were going to change some of the stuff in the Honeywell gear to make it simpler and get down the things. And at the time, I thought my arguments were what convinced Cliff and Joe. Well, what I now know is that they didn't need much convincing to think that a digital flight control was technically feasible, even though it was never been done in an aircraft before. And the reason is Cliff had been with DARPA, where he knew all about the Minuteman programs, and Joe, because he had sold the Air Force on using digital flight control in the Titan II, and then when that program got in trouble, this is when he was at AC Electronics, when that program got in trouble, he then went in to run the program and drove it to success. So both of them knew that it could be done, and really all they needed was the idea that if you applied it here, it would solve a lot of problems and what the benefits might be. And once that took over, it just went on. Now, the thing I don't know is how many closed-door discussions those guys held behind the scenes with people or their bosses to ease away. Knowing Joe, it wasn't too many. So then, having talked to North American, then my boss, Cliff Duncan, and then Cliff asked me to come work for him. And then he sent me up to MIT in Cambridge, alone, 29, to break the news to the instrumentation lab senior people that, well, they're not going to be primary for the onboard navigation. They're only going to have one computer, and they're going to do digital flight control. And to this day, I can remember going into the meeting, must have been on the second or third floor at 75 Cambridge Parkway, or 75 Memorial Drive. And there was Dick Batten and Dave and, a number of people there, all the senior people. And they started attacking the logic of what we were doing, naturally. And I became more and more and more of a midget among giants. I can still remember just kind of shrinking. And in the end, they accepted the challenge, and we all became good friends as we go on. But then we got back and in talking to the NASA network people, it was really kind of funny because I told them what the decisions were, and their reaction was, "Oh my God, I'm not sure that's the right thing to do." And it's now we've really got to deliver on what we've been talking about. But by then they were committed; they couldn't back out. And the stuff was even better than advertised. So with the command module decision made, then the next thing was the LEM. Well, we had Grumman with kind of the same situation. We had the same computer, so why not do the same thing? Grumman's a tougher nut than North American in those days anyway. And so this was talked about with Grumman, and they had seen this coming, and so they'd been off doing their homework. And they came in. There was a meeting, I think it was in May that spring, because all this stuff happened in 3 or 4 months. In May, and they came in and did a presentation, one of these big meetings. They knew in their hearts you couldn't control the vehicle as agile as the LEM. And so when they came in, they had done this study they'd implemented their autopilot design in the AGC, then for the LEM called the LGC. And they had access to the information. They'd actually done some analysis. I don't know how much programming they'd really done. They'd done some simulation, but it appeared to be a very professional, very thorough job. And they came in and they went through and how to do the LEM autopilot would require 90% of the cycles of the computer. And so I'm sitting there thinking, oh my God, if I sold this crazy thing that just won't work, you know, how am I ever going to live this down? And then George Cherry from the lab, he did the next presentation, and George was involved in the autopilot design, and I can still remember George standing up and saying, gee, you guys are absolutely right. You implement that autopilot in the computer, it will use up 90% of the cycles. But if you understand that it's a digital computer, and then you design for the capabilities of the digital computer, it will use up 12 or 13% of the cycles. And then he proceeded to go through exactly how that was the case. Well, at that point, I thought we were done. Okay. But there still were people absolutely convinced the DAP decision for the digital autopilot decision for the LEM would not work. A month or two later, I ran into one of the astronauts in the hall over in the astronaut building where I used to have an office, and this guy was not happy. He was not happy. When he started talking, I felt like I was right back in the Army being chewed out by an expert. Only this time the subject was my malfeasance in switching the LEM to digital flight control, because I was told in absolutely no uncertain terms that Grumman convinced him that the DAP would not work, would kill pilots, and that he would not fly with it, period. Just, I mean, I was chewed up one side and down the other. Now, I would note that he went on to land on the moon with the LGC between his hand controller and all the jets, and worked fine, and I think he even praised the performance of the DAP. And since I think there's about 12 people that could fit in that category, I won't say who it was. Now, as the systems then the lab was off doing their thing, everybody was doing their thing, reconfiguring systems and designing, this stuff was still percolating around, and it got all the way to the President's Scientific Advisory Committee. And so one of the issues that came up probably a couple of months, several months later, was we had to go up and justify why this was going to not degrade the reliability, why we thought it was going to work. And I wish I still had the slides I used for that meeting, but I can't find them. Now, the rest is history. The flight control certainly improved the mission flexibility. It saved fuel, was more reliable, never failed. And last but not least, without it, we wouldn't have been able to use the LEM engine for the Apollo 13 rescue. So I think we really owe Cliff Duncan and Joe Shea a tribute that they've never received for their courage in moving to digital flight control. Without them, it wouldn't have been even considered, and I'm sure it would never have been approved. Now, once it got approved and once it got launched, it took hordes of very talented technical people who worked their hearts out and accomplished miracles to make it a reality, and it worked every time. And to give you kind of a flavor, I think the DAP, the digital flight control for the lunar module, was only 2,000 lines of assembler. So they really squeezed it in. And one of the things that Gordon, or wasn't mentioned earlier, Eldon didn't mention, was that the computer, see all this iron, that was a 70-watt computer, including everything. And so at the time, it was did a lot of things, but it was absolutely state-of-the-art for how much power it was consumed. And so thank you very much. Thank you there.
One or two questions briefly.
You?
Throughout that digital autopilot, the fifth and sixth derivatives were added to the whole range from range, velocity, acceleration. And after acceleration, I believe came jerk. And then the fourth derivative was called snap.
Okay.
But Alan Plumb had to go 2 steps further. And what comes after snap? Crackle and pump.
answer the first part of the question, I don't know. Because after the decision was made, I was off causing trouble in other areas, and while the people who actually knew something were making it work. Yeah, Elvin.
You didn't mention the implementation. Someplace else fit in there.
Okay, when I mentioned after Joe called in North American and I got sent to MIT, then the way it actually got done was Cliff Duncan set up a series of what they called implementation meetings, which were weekly. I think they were weekly meetings, weekly for a while, or every other week.
I got the weeks.
Yeah, at Houston, and it brought in the MIT people, the NASA people, and first we did it with North American and the North American and Honeywell people. And those are meetings to just drive through what the interfaces actually look like, electrically, logically, functionally. They very systematic minutes were kept. They fed into Dave Hoag's data book about how this stuff all worked. And it kept the decision, a lot of these things that tend to screw programs up from just hanging around. I mean, whether you're going to use transistors for the interface to switch the reaction jets, or whether you have to use magnetic core coupling. And we had, you can imagine, using the same piece of GFE equipment in a system with North American and Honeywell, and in Grumman with RCA, and since it also had to feed Marshall, we had those interfaces down to the instrument unit. Those were not without their contention, but it was the management structure that just had them and drove the decisions. Not everybody liked all the decisions, but they got made.
David, what was Honeywell's reaction to getting shut out? Did you have to break that news to them?
I don't know. I mean, they ended up with, they still had a substantial part of the stuff. The only thing they got cut out of was about 6 or 8 gyros and some circuitry, and they had to add in some. So they didn't get cut out of too much. It was Autonetics got cut out for the reentry display, and that was a big. And the other thing was North American didn't fight too much because they didn't have a solution. In the LEM, they thought they already had a solution. Now, as it turned out, in the LEM, they were greatly wrong about how much the LEM was going to weigh, and so every possible ounce was squeezed out later. But so it's a good thing we did this when we did. Okay.
I think we'll have time later on